I saw most of AGR resistors are 5 amps and not 10 amps. When do we see 10 amps?
If you're a resistive current, where we use a lot of 10 amps is if there's a lot of capacitance in your network. So if you have a vast 600 volt or a vast 480 volt system and you have multiple sources, you can have more than 10 amps in your fault current. The resistor itself, it depends on you whether you use a 5 amp or a 10 amp, but you must make sure that you check to make sure that the capacitive charging current is less than the resistive current. We do 10 amps at times, not often, but mostly they are 5 amp, but we can do 10 amps at times.
Can we have neutral loads in HRG system?
Oh, you know what? That's a tricky question. Can you have neutral loads? Okay, in US, no. Prohibited to have distributed neutral on a resistive grounded system. In Canada, much to my disbelief, you are allowed by code to have a resistive grounded system. Although I really don't think it's a good idea because I think it's dangerous. And the difference is you have to trip on the currents of the first fault, right? Because that neutral point is going to elevate to 347 volts or 277 volts, but you can have a distributed neutral by code in Canada if you follow the Canadian electrical code. Second thing, you can have a distributed neutral in Canada if you're doing metering. If you look at section, I think 6-412 or 8-412, you can distribute your neutral to the metering PTs for metering purposes, but that neutral has to be insulated throughout the entire length. It can't touch ground, because if it touches ground, you actually have a solidly grounded system. So yes, by code, you're allowed to have a distributed neutral. Practically, I would not recommend it.
When with zigzag transformers are used, we must count both the resistor and the zigzag transformer resistance when calculated the fault current.
Correct. Now let's look at the zigzag. The resistor, it's easy to calculate the resistance of the resistor in ohms because you're purchasing a X ohm resistor. With a zigzag transformer, it's much harder to determine the amount of resistance you're going to have. And you have to get this from the manufacturer of the Zig transformer or your neutral grounding resistor supplier, such as me. You have to calculate the X over R ratio and the impedance at test per phase of the zigzag transformer, and then you can calculate what the impedance is of that transformer, and then subtract the resistance, the impedance, not the X, but the R part, from the resistor to limit the fault current when you have a fault to the desired value. We can have another session on this later because it's going to take a while to explain it. But the impedance of the transformer primarily when it comes to low resistance grounded systems, because IEEE states that you can limit the fault of a low resistance grounded system transformer to 3% of its rated value. So again, it's hard to explain without the pictures. We may have to have a discussion of that later on.
Could you speak further about charging current and how to calculate?
Oh, calculating the easiest thing to do with the charging current is give me your single line diagram and your cable schedule, and I can calculate. I have a spreadsheet where I put in all the information. Most of your capacitive charge is going to be the length of cables you have. So think of a conductor as really a capacitor, because you have the copper or aluminum conducting part, which is at one potential. You have ground, which is another potential, and you have the insulation of that cable between them. So this is two potentials isolated by an insulated medium. So you have a capacitor, but that capacitor is distributed throughout your entire facility. And that's why cable manufacturers give you the capacitance of your cable in capacitance or microfarads per 1,000 kilometers or per 1,000 feet or per kilometer, not thousands kilometers. So with that, we can calculate what the capacitive current is in your system. So you can realize if you had an ungrounded system here, we can actually put a fault on A phase to ground, and we can measure at the point of the fault only what the capacitive charging current is. If you have a fault on a resistive grounded system, you can measure the fault at the point of the fault, the current at the point of the fault, and the current through the resistor, and we can calculate what the charging current is because we have this formula. Capacitive charging current also exists on a solidly grounded system, although it doesn't really matter because when there's a fault, you're going to have a ton of current, and the neutral is never allowed to elevate. The reason why we look for the capacitive charging current is to limit the overvoltages of your system. So with a resistive grounded system, we guarantee that your voltage elevation of the unfaulted phases is only going to be at 173% of rated, so with respect to ground. So instead of having 347 volts to respect to ground, you're going to have 600 volts with respect to ground. On an ungrounded system, because there is no resistive charging current, there is no limit when you have intermittent arcing faults in your ground network or in your network. And most of the time you're going to have intermittent arcing faults repeatable is in a motor. So your escalation of voltages becomes unpredictable.
Would you compare the performance of the resistor type NGR versus reactor type?
Okay, so for a resistor, the resistor is looking to limit fault current to a specific value. And in that case, we dissipate the electrical energy into thermal energy. With respect to a reactor is looking to cancel out the ground current that is coming through the ground return path with an equal and opposing vector. So a reactor needs to be very specifically sized in accordance to the system and the prospective fault current that would be available. Now, reactors at the moment for Canada are very difficult to monitor for resistor faults, where if we have an open circuit on a reactor or a short circuit on a reactor, it's very different in terms of detection than on a resistor. Reactors, because they're involving an inductance, it's harder to monitor for those open and short circuit scenarios. Now, one of the questions here is, what is charging current? And I believe that was basically explained on this previous slide here. So charging current is based on the idea that capacitances exist between the conductors and ground, and we're looking to determine how this capacitance, which is throughout the entirety of the system based on the cabling leading from the source to the gear and from the gear to the loads, what that contribution will be to the total fault current IF. You can basically, we know that system charging current is dictated majorly by the cabling between the gear to the loads. So on a bus that's feeding multiple feeders, you would need to analyze the cables for each of those feeders and determine their overall capacitance to figure out how much charging current you have. Why is there an upper limit for the change of resistance with temperature? What are implications of letting the resistance increase? When we have a drastic increase in temperature, look at what happens to our current. So for example, for this 400 amp 10-second rated resistor, when we had this 304 alloy or the 430 alloy, we see that because the resistance is increasing, our current decreases to 189 amps. But the consultant specifically selected the 400 amp NGR in order to basically coordinate with his downstream feeder protection. His downstream feeder protection is set to pick up on a certain level of fault current discrepancy. So for example, if he has a relay that's looking for 300 amps of fault current discrepancy, he selects the 400 amp resistor so that there would be enough fault current discrepancy to pick up that fault. But if he's using a insufficient alloy here, then the current decreases drastically below the fault setting that's at the feeder level. And as a result of that, we will have the main breaker tripping and we will improperly impact our coordination aspect with respect to this fault current. That's the reason why we need to select a really nice alloy such that the current doesn't decrease and impact as severely as the other alloys on the market. What are the implications of letting the resistance increase? As we increase the resistance, conversely, our current will decrease, and that can impact our coordination. It might not be as important for high resistance grounding, where we're not really dealing with as much of coordination aspects, since we're kind of holding the fault in the system for an indefinite period. But for low resistance grounding, yes, it does play a very important role. When zigzag is preferable to star or broken delta. So broken delta is based on utilizing PTs to limit a fault current and having a resistor on the secondary of those PTs to limit the fault current that's occurring on the primary based on the imbalances of voltage. In this case, the zigzag for an ungrounded system, it's better to use a zigzag because it's easy to monitor the resistor from the XO point to ground than it is on a broken delta. But the broken delta does provide the same kind of benefit. It's kind of tough to find the PTs though that would be high enough VA rating to suffice the energy required to limit, whereas the zigzags can be sized in accordance to the current that you're limiting to at the neutral. So we found that the selection is better with the zigzag rather than in the broken delta where you're dealing with higher kVA ratings for your single phase PTs that you need to utilize. Since NGR resistor is mostly applicable in medium voltage, low voltage systems, how critical it is for charge current control, and/or is NGR resistor also used in HV systems? So one of the largest NGRs that we've ever had was a 69 kV, 1500 amp, 10 second rated resistor. I think that's the highest that we've gone. So I don't think it's utilized as much for high voltage. I think at that point, what I've seen at least is that they're using reactors instead of resistors for the higher voltage systems. The charging current control is important to reduce the transient overvoltages occurring on the unfaulted phases when a ground fault does occur. In sizing that resistor in accordance to the charging current of the system, you're basically controlling those transients. If we exceed the line-to-line rating of the cable, what happens is those transients can puncture the insulation and create more ground fault issues for the customer. So that's why it's important to size the resistor in accordance to the charging current. Even if you're tripping on first fault, that momentary transient on the unfaulted phases could further degrade the insulation on that cabling or on the equipment to pose additional levels of issues and may even impact the product's life cycle. How do NGRs compare to zigzag transformers when it comes to fault protection? Can you implement both? So we have been involved in a lot of projects involving zigzags in combination with neutral grounding resistors. Some customers end up using zigzags with a solid connection to handle an impedance to ground, and that zigzag will limit the fault current to a specific value based on its zero sequence impedance. But what we've been doing is we've been doing a combination of both so that we can pair off our resistor's resistance, which is fixed, to the X over R ratio of the zigzag and its associated zero sequence impedance, such that we don't have to size the zigzag incredibly high. This allows us to control the kVA rating of the zigzag with respect to how much current that the resistor is limiting the fault to, if that makes sense. And in doing so, we've been using this combination for various projects across Canada and United States, and we also use it for our hybrid high resistance grounding approach, where multiple generators are paralleling with each other. For grounding a delta connection, we use zigzag, as you mentioned. Are there certain specs to consider for selecting this zigzag transformer? Do you provide assistance with such configurations? Yes, we can assist you on that. For low voltage systems, typically we use a 5 kVA zigzag, since we're typically limiting to 5 amps or 10 amps on a low voltage system. We know that if we're limiting to 5 amps, that current will split up into 3 sections. once it hits the phases of the zigzag. So that's about 1.67 amps that the zigzag has to handle for a continuous rating along its 3 phases. And from that case, you can basically size the zigzag in accordance to how that current ends up splitting up. So for example, even in the case of, let's say, a 200 amp 10-second let through current that we have selected for our resistor, the zigzag would have to be able to withstand 67 amps for 10 seconds on each of its phases. Is there any preferred limit for the overall ratio X over R given by the zigzag connected to the NGR? Typically for grounding transformers, you would use somewhere, I've used an X over R ratio of 2, but in most of my projects, I've used something that is 4 or greater for that X over R ratio. And that was coming off the recommendation coming from our transformer manufacturer saying that grounding transformers should have a higher X over R ratio. What devices are available to monitor this neutral grounding resistor in a system with the neutral connected to ground? We have our I-Gard Sigma 3C, which can monitor the resistor for both open and short circuit conditions, as well as for ground fault. We sell this product alongside our neutral grounding resistors to monitor and to meet code requirements stipulated in Section 10, Grounding and Bonding of the Canadian Electrical Code. For the neighbors down south in the United States, they don't have a requirement for resistor monitoring. Their only requirement is strictly for ground fault. But we've been in the process of convincing customers in relation to the benefits of having open and short circuit detection. For example, if your system ground is strictly dictated by this XO to ground connection with the resistor, in an open circuit scenario where we lose that system ground reference, our system is essentially ungrounded, and that impacts your protection scheme downstream. Conversely, if our resistor is shorted, then we're in a solidly grounded system, and our ability to limit the likelihood of an arc flash incident goes down significantly because now the current is not being limited and it can go to thousands of amps. In this case, your system will either trip on the first fault or you have a more problematic situation on your hands. How the capacitive charging current give rise to false tripping of healthy feeders, tripping when there is single line to ground fault on eject feeder. One sec. How the capacitive charging current give rise to false tripping of healthy feeders, tripping when there's I don't think that that's what will occur. The charging current is only going to go to the path of the fault. So if that's the case, the circulating current is not going to go all through just the capacitive charging current coming from an adjacent feeder that's healthy. It's going to be all the distributed capacitance, which is very, very low level fault current. Very, very low. Majority of the fault current is going to flow back through the NGR path, right? And it's going to go back to the point of fault, which is where that zero sequence CT is going to pick up that circulating current and that imbalance. And as a result, it's not going to impact the healthy feeder that's adjacent to the faulted feeder. Only the faulted feeder will pick up the fault, and that's it. One of the equipment used in high voltage systems is called four-legged reactor. That is a Y-connected reactor with a grounding reactor in the neutral. I don't think that there's a similar concept about resistors, just probably because the four-legged reactor, you're basically asking for a transformer with a reactor from neutral to ground, if I'm not mistaken. In most cases, we pair with like transformer manufacturers and they buy the neutral grounding resistor from us and then they sell that transformer with the resistor as a package, but they don't typically call it a four-legged reactor in our case because it's not 4 inductances, it's actually 3 inductances with a resistor. So they'll just call it a resistance grounded transformer. That's what we would call it, at least. For a 33 kV line-to-line sub-transmission system, is it common to assume a max 1 Ka solid neutral grounding resistance resulting in 19.1 ohms resistor? Is that the best practice? Well, it really depends on that 33 kV substation and its associated cable lengths and so on. 1000 amps, that's a lot of fault current, and I don't think that the charging current's going to be that high. But you may also need to do some simulations in ETAP to determine if that is the correct selection to take based on the capacitance in your system and the other things that are connected in that system. What you don't want is to put a resistor in a system where upstream of that system, there's a solid ground connection intertwined in that same system. If you have a solid connection here and a resistance grounded connection here, you're going to have issues with respect to how high the fault current is going to get, because the fault current will see two paths it can take, and it's going to choose the path of least resistance, which is that solid connection. And that can play an impact on how much current that you're also seeing at the resistor that is downstream. So yeah, to answer the question, it really depends on the system. So it can't be said for certain that 1 kA would be sufficient or not, depending on how big these lines are. Charging current is directly proportional to the line-to-line voltage of the system. So as we increase that voltage, we're going to have more capacitive charging current in our system. Based on your experience, what is your solution for the substation's internal voltage source? Zig-zag secondary star or separate station transformer? What we've seen in our experience is that the customer would typically, for substations, they would typically connect the resistor directly off the neutral point. The only cases that I've seen the zigzag and the resistor combination utilized is if they're having multiple generators going to a paralleling bus and they're looking to make sure that that paralleling bus has a ground reference. Alternatively, I've also seen a situation where if the system is delta, then they would use a zigzag to establish an artificial neutral so that they can place a resistor to ground. Those are the situations that we've seen the zigzag being placed. Okay, so from the same person, I want to have zigzag in differential 87 zone. What is the practical rating zigzag branch in normal network unbalanced? The rating of the zigzag is dictated by how much resistance let through current that you have from the neutral to ground of that zigzag. So that's going to dictate the rating of the zigzag. We can provide 87G differential relaying on the zigzag through the use of monitoring the three phases as well as the neutral incoming and outgoing current to see if there's an issue with the zigzag itself, if one of the legs is faulted or anything like that. Other customers, to satisfy section 26, have been using overcurrent as well as loss of phase protection through blown fuses, and also using a fuse monitor to monitor when the fuse gets blown. Is a zigzag grounding transformer preferred over a delta Y grounding transformer, or would the specific application determine which type of grounding transformer would be preferred? There's no advantage over using a zigzag or a delta Y. If a neutral is readily available, just place the resistor off the neutral. If you have an ungrounded system and you need to establish a neutral, use a zigzag. Star for internal voltage of substation. Okay. Every power system expands with time, so how to find adequacy of the NGR? If you size the resistor and you know that there's future feeders that are going to come in, put some margin of space available based on what your charging current is existing, and estimating that, hey, if this feeder is, let's say, in the worst case, 200 feet in length with this amount of conductors, how much does that change my charging current? And then you size your resistor in accordance to a bit of a higher value to also accommodate those future feeders where that expansion occurs. For the comparison between NGR and NGT, an NGR is doing the same thing as an NGT, but an NGT is very difficult to monitor with the new Canadian code requirements. So right now an NGR is probably the better option because we can easily monitor that, whereas the NGT, because it's a transformer-based solution with inductances, it's much more difficult to monitor. Are liquid neutral grounding resistors still used? I have never encountered a liquid neutral grounding resistor, so I don't think I can answer that, because in instances where we're dealing with voltages that are but beyond 5 kV, we just use a solid dry type NGR, I guess, because the NGR is doing nothing in normal operation. It's only when there's a ground fault where that resistor will see current. So in most cases, there's no need for liquid cooling resistor unless you're holding the fault current indefinitely. For low voltage systems, the box already is so small that liquid cooling it doesn't really provide an advantage, because our resistor is it's really small. It can be floor mounted, wall mounted, and it doesn't need to have liquid cooling in this case.